Hello, pre-calculus friends. This is Miss Backfish, and I am here to talk to you about solving trigonometric equations. Okay, and for those of you in my dual enrollment, this is section 5.5. Sorry, trigonometric. I was going to say sorry that Google Docs doesn't know how to spell trigonometric, but they did. It was me. All right, so we're going to look at three different types of problems really in this section, and the first one is just really making sure you got the gist of what we're doing here, and that is saying, here's a solution, maybe. You check it. In other words, it's given as use substitution to determine whether this particular value of x is or is not a solution of this trigonometric equation. So you're pretty much just checking. You're plugging in cosine of pi over 6. What's cosine of pi over 6? Well, that's root 3 over 2, so no, it's not. That's not 1/2. Okay, so here's another one. Very similar idea. Just plugging in to see if this makes a true statement or not. Cosine of 2 times pi over 6. Well, that would be cosine of pi over 3, and the cosine of pi over 3 is 1/2. Now on the other side, this is sine of pi over 6. Sine of pi over 6 is also 1/2, so yes, it is a solution. So that's all you're doing in the first couple of questions in this section, is just confirming whether or not the given value of the angle is a solution. Now after that, that's where things get interesting, okay? And when you are solving trigonometric equations, pretty much no matter what text, no matter what class you're doing it in, there's one of two things that you're being asked to do. You're either being asked to solve the equation on a given interval, and I'm sorry I wrote this wrong, that should be a parentheses. Okay, on a given interval that is basically the interval of 0 to 360. One circuit of the unit circle pretty much. Just your basic unit circle values, or you're being asked to find all solutions. So let's look at one and see the difference between that. Let's suppose I am asked to find sine of x equals root 3 over 2. Okay, now if I think about the unit circle, there are two places that come to mind that the sine of x is 3 over 2. Okay, and that's the ugliest unit circle ever, but basically right here at pi over 3 and right here at 2 pi over 3, both of those I have a y value of positive root 3 over 2. If we think about that 30, 60, 90 triangle, here it is. The coordinates for this point are 1/2 root 3 over 2 and negative 1/2 root 3 over 2 over here. And remember, your sine value is your y value. So those are the two locations I can think of when I think of the unit circle where the sine has a value of square root of 3 over 2. So are those my two answers? Well, that depends on how the question has been asked. If the question has been asked, and I'm really sorry about this circle, that's really kind of embarrassing. If the question is asked this way, this is saying basically give me the unit circle values where this is true. And I want you to notice, and I'm very sorry I wrote this wrong, I'm apologizing all over the place here today. Let's do this. I want you to notice how this is written. It's written with a bracket on one side and a parentheses on the other. And the reason is that 0 and 2 pi are both the same location. 0 and 2 pi are both right over here. Okay? So we have to know which one of those to use if the value we're looking for is right here. Brackets mean include this. Parentheses mean don't include this. So this is telling me that if we want this location, we should use 0, not 2 pi. Okay, so that's what that's saying. So it's basically everything from here to almost back to there, but if it's all the way back to there, we would call it 0 instead of calling it 2 pi. So if I were asked to solve this on the interval 0 to 2 pi, I would say, okay, x is pi over 3, and x is 2 pi over 3, and that's it. That would be my solution. So this is on the interval 0 to 2 pi. If instead I was asked to solve the exact same equation for all solutions, now things get a little bit more interesting, okay? You got to think back to when we first talked about coterminal angles. There are infinitely many angles where the terminal side of the angle would come to the same spot, would end up right here, and the same goes for right here. In other words, for instance, 7 pi over 3. Well, 7 pi over 3 is all the way around. 6 pi over 3 is 2 pi, plus another 1/3. Boom, it's right there. How about 13 pi over 3? Same place. How about negative 5 pi over 3? That would be going this way. Same place. There are infinitely many ways I can describe this particular location. There are infinitely many ways I could describe this location. And it's not like we could possibly list them all. So if we're being asked to list all solutions, we have to get a little bit creative. So here's how we do that. This is sort of over in my space. I will get rid of it. All solutions, the way I would say it, is I would say, well, let's start with the ones that are on the unit circle. Let's start with those basic ones that I would answer if you only wanted the unit circle values. And then say, okay, coterminal angles basically happen when I go all the way around the circle and get back to that spot. All right? All the way around the circle is 2 pi. 360 degrees is the same as 2 pi. So this plus 2 pi would get me back there. Plus 2 pi twice would get me back there. Plus 2 pi 3 times would get me back there. Or how about minus 2 pi would get me there? Minus 2 pi twice, minus 2 pi 6 times, minus 2 pi 20 times. So what we're going to say is plus 2 pi however many times. This is an n. Sometimes we use a k, but it's basically just a variable to say however many times you want to go all the way around the circle from that point, positive or negative, you'll get back to another solution. All right, same thing here, plus 2 pi n is what we're using in this textbook, but a lot of times people use k. So when you are asked for all solutions, you need this. Okay, now this is a sine problem. It's a little bit different if it's not sine in some cases. So here's what I want you to think about. All right, graphing. Remember when we did sine waves and we did cosine waves? Basically, we did the good old sinusoidal function. The place here, something like this would be root 3 over 2. So here it is at pi over 3. Here it is at 2 pi over 3. And then we go and we get there again. And then we get there again. And so on. And we would get there negative. We would get there again. There are infinitely many places where my y value is 2 pi over 3. I'm sorry, where my y value is root 3 over 2. Excuse me. Root 3 over 2. So that's what it looks like with sine. Now, with sine, remember that the period is how long it takes, or the amount of x value that it takes before it starts to repeat, to go all the way through the curve, to get all the way through one cycle of the curve. And after this, we would do same thing again. We would be repeating. So this is one cycle. The period for sine is 2 pi. So that means every 2 pi, I'm going to get back to the same place. The period for cosine is 2 pi. So every 2 pi, I'm going to get back to the same place. The period for cosecant or secant, which go with sine and cosine, all have a period of 2 pi because that's how long it takes me in terms of x values. That's how far on the x-axis I have to go before I get back to the same spot. But what about tan? Tan and cotan do not have a period of 2 pi. So let's look at a tan one. Let's say tan of x equals root 3. And think about where that would happen on the unit circle. Let's see if I can draw a better circle this time. It's a little better. Okay. Tan of our angle is root 3 when our angle is right here at pi over 3. because the coordinates here are 1/2 root 3 over 2, and remember tan is the same as the sine over the cosine. Or the other place the tan is positive root 3 is right down here at 4 pi over 3. This is negative 1/2 negative root 3 over 2, which would also give me sine over cosine would give me root 3. So again, if I was being asked to solve it on the intervals 0 to 2 pi, my answer would just be these two angles. And I would stop. If instead I was being asked to solve it on, or give all solutions, well, every time I go all the way around the circle, in either direction, I get back to this spot again, basically, and it has a different name. But notice that if I go just halfway around the circle with tan, I get to another spot that has the same value. That goes with the idea that unlike sine and cosine, the period for tan and cotan is 1 pi. Remember that when we were doing graphing? So instead of going 2 pi to get to your other values, and you don't even have to name both of these, this is 1 pi. Half of the circle is 1 pi. So if I just name the first time it happens, I could say x is pi over 3 plus 1 pi, 2 times 1 pi, 3 times 1 pi, 4 times 1 pi, or negative 1 pi, negative 2 times pi, plus pi, the period, times whatever number you want to give it. However many times you want to go around the circle 180 degrees from this spot, pi from this spot, you will get to another angle that has the exact same tangent value. Okay, so again, you have to add this little part when it's all solutions, but for tangent and cotangent, it's only 1 pi times n, or 1 pi times k, versus everything else, sine, cosine, secant, and cosecant, it's 2 pi times n, or 2 pi times k. And it's really just your teacher, your textbook, your program as to whether it's an n or a k. It could be anything. It doesn't matter. It could be a c. It could be a, I don't know, an asterisk. It's just however many times pi. That's what it's saying. All right, so let's do some more problems keeping that in mind. Okay, here we go. We've got find all solutions. So find all solutions means I have to include that plus 2 pi k, or plus 2 pi n. And I know it's 2 pi, not 1 pi, because it's sine. So first I have to think about the unit circle. Where is sine equal to negative 1/2? Now remember, sine is the y value. So we're thinking, where is y negative? So we come downward, over here, and over here. So it would be in the third and the fourth quadrants. Negative 1/2, it's going to be (30 degrees below. Sorry, those don't look even. But it's going to be 7 pi over 6, and it's going to be 11 pi over 6. Okay, so my value is 7 pi over 6 plus 2 pi times n, and 11 pi over 6 plus 2 pi times n. And that's my answer. What do you know? I accidentally did the problem that I had set up for us. So let's just change it. Let's say, boom. When is tan of x or theta, or whatever your angle is, equal to root 3 over 3? Where is tan positive, first off? Tan is positive in the first quadrant and in the third quadrant. So that's where I'm looking. So I'm thinking tan is positive here at pi over 6, because the coordinates here are root 3 over 2, 1/2. And if I put this over this, I get 1 over square root of 3, which rationalizes this way. And I come over here directly across from that, 180 from there, and I'm at 7 pi over 6, where it's negative root 3 over 2, negative 1/2. Okay, and again, negative 1 over negative root 3 rationalizes as root 3 over 3. So I'm going to say x equals pi over 6, and then I'm going to say plus pi times n. 1 pi times n, not 2 pi times n. And since that covers this point, because if I take pi over 6 and add 1 pi, that's the same as adding, this is 1 pi. Then that covers this point also. This is all I need to say. And I'm done. Okay, so we've been working with ones that were just pretty basic, straightforward, the angle. And now we're going to start looking at things that have a little bit more of an equation situation to them, where we need to get it to where our sine or our cosine or whatever is alone. We need to isolate it, or maybe factor it. Not on this one. On this one, we just need to isolate it. So I'm going to say, let's move this guy over here. I need to get it where its sine of some angle equals a number. I need to get the sine of theta all by itself. So this gives me 1 equals negative 2 sine theta. Still trying to isolate sine theta, I'm going to divide both sides by negative 2. And I get sine theta is negative 1/2. So I have to think about where the sine is equal to negative 1/2. We just did that one a second ago, didn't we? Let's see. Boom. That's where. And we are still doing all solutions, so we're going to say the exact same thing. So x is, it's theta this time, is 7 pi over 6 plus 2 pi times whatever. And theta is 11 pi over 6 plus 2 pi times whatever. Okay? Again, sometimes people get confused by this whatever I'm saying here. This doesn't need to be, this is not something we need to find. This is not something that you're going to plug in and find out what it is necessarily. The point is, I could plug in any integer, any positive or negative whole number. 1, 2, 3, 4, 5, 6, 7, negative 1, negative 2, negative 3, negative 4, etc. And it would give me a value of theta for which this equation would be true. Okay? So it's just a generic way of describing all of the values. Now we're going to switch over to solving on that limited interval, which is basically just one rotation of what we usually think of as the unit circle. Okay, so tan of x over 2 equals 1. Now, what's interesting here, you might first instincts might say, I need to multiply both sides by 2. But it's not the tangent of x all divided by 2. It's not this. Okay, see the difference? This is part of the angle we're taking the tangent of, so we can't really do that. So what we do is this. We treat it like it's just whatever, the whole thing here is my variable. In other words, I'm going to say, let me pick another, I'm going to call it, let's do theta. Let's say tan of theta equals 1. And I'm going to solve that, and then whatever I get for theta, I will set it equal to x over 2 to find x. So the tangent of theta is 1. When is the tangent 1? It is 1 at 45 degrees, or pi over 4, and again at 5 pi over 4. So theta is pi over 4, theta is 5 pi over 4. If you don't believe me, take your unit circle and put sine over cosine, y over x, all the way around and get your tangents so you can look at them. Now, that's what theta is, but we were asked what x is, and x over 2 is equal to theta. So I'm going to say x over 2 equals this. X over 2 equals this. And then cross multiply to solve, which really in this case is multiplying both sides by 2. So I get x equals pi over 2, and here I get x equals 10 pi over 4 is 5 pi over 2. And those are my values. Maybe. Hold on. Stop the party. Why? Because I need to check this. I was asked to solve on this interval, right? This value is not on this interval. Okay? Remember that 2 pi, if I have 2 in the denominator, that's the same as this. So this is more than 2 pi. So this is not on that interval. So this becomes my only solution. Okay, so now we ramp it up a little bit. All right, this, you'll notice, looks significantly more complicated, and that's because it's basically a quadratic. Look at this like it says this. Okay, we're solving for cosine theta, basically. We're trying to get cosine theta alone so that we can find out what cosine is. So we can find out what theta is. But first we have to get cosine theta alone. So we can think of that as being sort of our x. That's exactly what this is. This is 2 times cosine theta squared plus cosine theta minus 1. So in this respect, it's our x. So how would I solve this? Well, I would factor it. 2x times x gives me 2x squared. I know it's going to be a 1 times 1 that's going to give me a negative 1. One of these has to be positive, one of these has to be negative. I would just make sure that I sort of thought about it and checked. If this is positive and this is negative, that makes 2x minus 1x, which gives me a positive 1 here. So this is how I would factor that. And then I could set this equal, take each factor and set each factor equal to 0, like so. Okay, so that's what I'm going to do here. Remember we said that our cosine is the same as x here, so that means this is 2 cosine theta minus 1 times cosine theta plus 1. So that's how I'm factoring this. 2 cosine theta minus 1 times cosine theta plus 1. That equals 0. So now I'm going to set each of those factors equal to 0 and solve. Didn't give myself much space here, did I? Okay, so I want to know here, where does cosine of theta equal 1/2? And we're answering this on the unit circle. Where is cosine theta 1/2? Cosine theta is 1/2 at pi over 3 and also at 5 pi over 3. Okay, let's set this one equal to 0 and solve. Where is cosine theta equal to negative 1? Well, that would be at pi. And that's it. Those are my answers. You can always check your work when you're solving. Plug them back in, make sure they work. Also, always check that your answers are indeed on this interval, which they are. All right, next up. 4 sine squared of x plus 2 equals 0. Okay, so again, I'm going to think of sine of x as being sort of like my x. In other words, this is 4 times something squared plus 2 equals 0. Well, if I had to solve this equation, I would subtract 2 from both sides, divide by 4, and take the square root. That's what I'm going to do here. Subtract 2 from both sides. I'm going to come up here to see if it gives me a little bit more room. Well, let's start here first. 4 sine squared x equals negative 2. Now we'll bring it up here. This gives me sine squared x is negative 1/2. Okay, so now I need to take the square root of both sides. All right. Sine of x equals, right? Because we have a negative inside our radical. How do we deal with a negative inside the radical? We have I. So are we going to have sine of something equals I? Well, think back to the sine graph. It's all real. The sine is always going to be some number between negative 1 and positive 1. It's never imaginary. I mean, vertical shifts could make it some other number or stretch, but it's not going to suddenly become imaginary. So I'm going to say it's undefined or no solution, depending on how it's phrased on your assignment. What if, just for argument's sake, what if it had said sine squared is positive 1/2? Oops, sorry. Yeah, let's rewrite that. Sine squared is positive 1/2. Okay. Then we would have taken the square root of both sides. Then sine is square root of 1 over the square root of 2. Square root of 1 is just 1. And it helps to remember that when we first developed the unit circle, this was what we got using our 30, 60, 90 triangles, and we just changed it to this. So this is what this says. Where is the sine of x equal to square root of 2 over 2? So that would be at pi over 4 and at 3 pi over 4. It's a shame this is not what it asked me, but no, it has that negative there, and so I have to say, I'm sorry, that's not going to happen. All right, next up, these to me are kind of interesting. Notice that you've got two different trig functions. Pretty much when you have two different trig functions and you're trying to solve, you need to get it down to one trig function. Okay? Or perhaps you're going to have two parts. And that's kind of what happens here. I can factor a cosine out. I have a cosine in both of these expressions. So I can say cosine of x times 1 minus sine x. So now I've taken them apart. So now I have two different parts I can solve, and they're in the two different trig functions. So that's going to work out okay. So this gives me cosine x equals 0. Where does that happen? That happens at 0. Remember, it also happens at 2 pi, but we were told to do it on this interval, which means it's closed on 0 and open on 2 pi, meaning it does not include 2 pi. It does include 0, so I'm going to put 0. And then here we've got 1 minus sine x equals 0. Subtract 1, negative 1 sine x equals negative 1. Divide both sides by negative 1, and you have sine x is 1. Where is the sine 1? Well, that happens when x equals pi over 2 at 90 degrees. So those are my two answers, and I am done. That was number 9 here. And last but not least, we have another one that looks like I need to factor, but oh no, it's got a sine and a cosine, so what am I going to do? Well, I'm not going to be able to factor it. I cannot look at this and go, oh, that's... Let me just rewrite it, because I'm at the bottom of my page, and I'm going to run out of space pretty quickly here. I can't look at that and say, oh, that's 2x squared plus x minus 1, because it's not. This is not the same thing that is squared here. They're not the same thing. Okay, so I can't do that. So I'm not going to be able to just factor it. I have to figure out a way to make this all the same trig function. And I'm going to rely on my standard good old Pythagorean identities. In other words, I have a sine squared here. Remember that sine squared plus cosine squared is 1. Which means that sine squared is 1 minus cosine squared. So that's what I'm going to do. I'm going to rewrite that as 1 minus cosine squared. So I have 2 times 1 minus cosine squared plus cosine squared minus 1. So I've got some simplifying to do now before I can do anything else. So distribute 2 minus 2 cosine squared theta plus cosine theta minus 1 equals 0. I'm going to go ahead and start with the quadratic term. And then 2 minus 1 is 1. Okay, now I don't like to factor with a negative as my leading coefficient. So I'm going to multiply through everything by negative 1 because it's equal to 0. I can do that and it'll still be equal to 0. So 2 cosine squared theta minus cosine theta minus 1 equals 0. Now everything is in the same trig function. In terms of the same trig function, I can think of this as being the same as this. And think about how I would factor that. So this is 2x times x. I know they're both going to be 1s. If I want the middle term to be a negative 1x, which is what I've got here, then I need the bigger number to be the negative and the smaller one to be the positive. So that's what's going to do it. So 2, if my x here is cosine theta, This is 2 cosine theta plus 1 times cosine theta minus 1. 2 cosine theta plus 1 times cosine theta minus 1. I have factored and I'm ready to set each of those factors equal to 0 and solve. 2 cosine theta plus 1 equals 0. That means 2 cosine theta equals negative 1. Cosine is negative 1/2. Where is the cosine negative 1/2? That happens at 2 pi over 3 and at 4 pi over 3. Over here we have cosine theta minus 1 equals 0. That means cosine theta is 1. Where does that happen? That happens at 0. So when theta is equal to 0. And those are my answers. Again, and always check at the end of the problem. Again, on this one, it was asking me on this interval. So I don't have to put the whole plus 2 pi k or plus 2 pi in. Hope this has helped you so much. I'll see you next time.